The lecture today is going to be about trigonometric identities. Let's just briefly explain what is an identity. In mathematics, you come across various relationships. Most common one are equations you study. Sometimes you come across inequalities. And occasionally you come across identities. What are examples of equations? Simple example would be something like 2x plus 3 is equal to x minus 1. The meaning of the equal sign here is essentially a question. Is there any value for x that makes the left-hand side be identical to the right-hand side? So the implicit meaning of this equal sign here is to find x. So find x so that what? Find x so that when you substitute it back here, you actually get a true statement. We are searching for x. Find x to make this a true statement. Inequalities are then built on the concept of equations. I might be asking you to figure out all the x's. Now there's going to be a range of values of x where in comparison of two quantities, one side happens to be larger than the other side. For example, 5x minus 2, maybe I want it to be larger than, say, x minus 10. Again, you are trying to find x to make this a true statement. It's just that the answers that you are finding to that is having a bit of a different flavor than you had over there. You find a range of values, and the two sides are not identical. Rather, one of them is larger than the other one. Identities are fundamentally different from these. Identities refer to statements that are always true regardless of what value of the variable you use. For example, if I write x plus 1 squared is equal to x squared plus 2x plus 1, the meaning of this is not a question of finding an x that makes two sides to be equal to each other. Rather, it's a statement that regardless of what value for x you pick, after you have done this, you get something that is exactly the same as what you have on the right hand side. So this is true regardless of value of x. Like for example, if I put 5 here, 5 plus 1 squared is equal to 5 squared plus 2 times 5 plus 1, because this is 36, and 36 is 25 plus 10 plus 1. Is there anything special about 5? No. Go ahead and try, say, 10. If you say 10 plus 1 squared, is that same as 10 squared plus 2 times 10 plus 1? Well, this side is 121. Right hand side 100 plus 20 plus 1, and it checks as it does here. There is no value of x as ordinary real number that's going to violate this statement. So that is fundamentally different from this one. A simple example of identity is to say x is equal to x. If I say x is equal to x, I'm not asking you to find x. It's not like that. if you process this thing further, if you like subtract x from both sides, you end up getting 0 equal to 0. So the equality that comes up in an identity is a statement that is always true. It doesn't have restrictions on values of x, except for perhaps to make the statements meaningful. Other than that, wherever the statements are meaningful, they are supposed to be equal to each other. So there are identities in algebra that you see in a college algebra class. They are called algebraic identities. The most famous of them is perhaps the following, that squaring identity. You see like x squared. Let me see if you can remind me the rest of this. What are the other pieces on the right hand side? 2xy plus y squared. That's a slightly more general case of this statement that you see. So again, here the statement is not go find an x or a y or both or something that this is true. Rather, we are saying this is always the case no matter what numbers x and y you pick. Another famous identity is the sum times difference identity. What is the right hand side of that one? X squared, and the other piece minus y squared. There is a whole list of these things that you come across in algebra class. What we are intending to do here in this section is to study trig identities. There's a very long list of these things. I'm afraid to say there's about 6 dozen of them. So it just piles up very quickly. And what happens is that all of them are useful. All of them show up here and there, but almost never in any kind of a concentration. Sometimes it's like stuff in your toolbox. They sit there for years until all of a sudden you need them, and then when you need them, you do need them. Then you need them for one day, and then it goes back to the toolbox until 2 years later, then again you need them. So problem that we are going to encounter here is that we are going to quickly go through a long list of tools. This one does this one does that, and so on. So you just see the tools. You don't get to do much with them other than just playing with the screws on them and opening and closing and such. You kind of need to remember the tools. Just like in your garage, you need to know where you place them so you don't go buy it again. Same issue here. Now, trig identities come in a variety of types. To get started, we have the Pythagorean identities. Pythagorean identities are directly based on what you remember as the most famous formula in mathematics, which I'm sure I can get a chorus out of you guys. For a right triangle with legs AB and hypotenuse C, this most famous statement says what? It says A squared plus B squared is equal to C squared. Remember I was telling you back home they call it the Bright theorem because that attracts more attention than anything else. Okay, Pythagorean theorem is built on this, except that trig names come into play, and then we have to use sine, cosine, tangent, secant, cosecant, cotangent, and so on to write this. Let's go ahead, explain one of them in detail, and for the remaining ones I'm going to try to be brief about it. So let's suppose this angle here is theta, and this is our right triangle. This is B, and this is A, this is C. Let's write some connection between these quantities. What was our definition for sine of an angle? its opposite over the hypotenuse. You remember we had this essentially very first day. I can rearrange this thing by saying that the opposite is equal to the hypotenuse times the sine of the opposite angle. Simply I multiply both sides by c. Similarly, we had cosine of theta is adjacent toward divided by hypotenuse. Again, I can rearrange this thing by multiplying with the c to say that the adjacent is equal to hypotenuse times cosine of the adjacent angle. Next, I can take this two relationship and square them in anticipation of putting it back here, see what we get. So if I square this, I'm going to get b squared is equal to c squared. Sine square of theta, square of this is going to be a squared is equal to c squared times cosine square of theta. Now I take these things, plug them back over there. That is, I say instead of a squared, let me put what it is equal to. That is c squared cosine square of theta. And instead of b squared, I put its equivalent, which is c squared times sine square of theta. And instead of c squared, I just write c squared. Now I see something nice happened. C squared shows up in every term. So from the left hand side, you can either factor c squared, or you can go ahead and divide your equation by c squared. So if I factor c squared, I get c squared times cosine square of theta plus sine square of theta. On the right hand side, I have c squared. So if I go ahead and divide both sides by c squared, I am going to be left with the following, that cosine square of theta plus sine square of theta is equal to 1. Okay, so that's a grandfather of all the identities we are going to be looking at, so it makes sense to put it on some attention. So sine squared plus cosine squared is equal to 1. Now let's go ahead and make a quick review of this so that we don't have to go through all of this thing every time. Suppose I want to remind myself what's going with respect to this identity, and I want to have everything in a little box. Here's how to compress all of this derivation. I say, let's take a triangle, and every one of these identities we go through, we are going to take turns making one of these sides to be 1. Here I take my hypotenuse to be 1. This angle is still theta. Now I have to remember quickly, if this is hypotenuse is 1 and this angle is theta, the opposite of it is going to be what? This opposite, in terms of trig functions, it is going to be sine of theta. You have to kind of have that in your mind, and it has to be quick, based on unit circle or based on definition that sine of an angle is a ratio of opposite to hypotenuse. If hypotenuse is 1, opposite has to be sine of theta. Similarly, the adjacent is what? Cosine theta. So now you have a right triangle. The length of each side is given to you. You can write the Pythagorean Theorem. Square of this plus square of that is square of hypotenuse. So I have cosine square of theta plus sine square of theta is equal to 1. Same thing. Now each of the identities that we write in the Pythagorean section can be written multiple ways. By just kicking the equation around, how you want to write it, just notice that these are all the same. Like if I were to write this as 1 is equal to cosine square of theta plus sine square of theta, it's not that this is really anything new. I just took the right to the left and left to the right. So we are not going to write both of them. It has to be immediate and natural to us to go from one to the other. Also notice that it doesn't make big news if I just rewrite one side of this equation a little bit different. Like if I write sine first and cosine next, it's the same thing, because when you're adding numbers, a plus b is same as b plus a. Okay? But there are some modifications that are a little bit less trivial than this, and you want to practice them. And those things are based on idea of isolating one of these three sides. Here, hypotenuse stands alone. Suppose I want to make the adjacent to stand alone. What would my identity read like? So I'm making this side separate from the other two. Tell me, what would be the right-hand side of my identity? We typically put the minus after the positive terms. So I just took the sign to the other side. Again, this is just twin brother of that one. It's not really any different. Or I might have decided to focus on opposite side for whatever reason. If this is my focus, I can isolate that. In that case, my identity is going to read as sine square of theta is equal to 1 minus what? Cosine square of theta. So we just list one of these things, and we expect that the students recognize that these are all talking about the same thing. Any identity can be focused on any one of these three sides. Just remember that you have that option available to you. Now, we are going to modify this identity in several directions. One of them is to say, perhaps the application that I have in mind will take the adjacent to be 1. This angle is still theta. If adjacent is 1, what is the opposite? Remember? Say it again. You have to, so this is a question mark. What function connects this angle, opposite and adjacent? Tangent of theta is equal to, so let me call this thing some quantity like h. Opposite over 1. So the opposite is equal to tangent of theta. Again, this is something that we saw in unit circle approach. If this is 1, opposite is going to be tangent of theta. So far, if this is theta, this is 1, this is tangent of theta. Next, do you remember any kind of definition that connects these three quantities, this 1, theta, and this guy? Let's call that one L. I want a definition that, okay, cosine will work. What else would work? What is the ratio of a hypotenuse? I want this to stand in the numerator. What's the ratio of hypotenuse to the adjacent? What did we call this? Hypotenuse divided by adjacent is secant theta. So that hypotenuse now is secant of theta. So if I take my angle and call the adjacent side of it 1, the opposite automatically becomes same as tangent, and the hypotenuse automatically becomes secant. Now, any right triangle, however you want to name the pieces, still satisfies the Pythagorean identity. So, tell me, in this case, how would that identity look like? You remember, square of one side plus square of the other side is square of the hypotenuse. So what do I say? 1 squared plus tan squared is equal to secant square of theta. So this is the second form of Pythagorean identity. It's really not all that different from that one. Just a different worldview we have leads to this equation. It's still, we are just saying a squared plus b squared equal to c squared. Before we go any further, let me make sure you understand what this notation means. Let me ask you guys, when I write cosine square of theta, what does that squaring mean? What is it that I'm squaring? This thing is a shorthand for the following activity. Take an angle. Take its cosine, like press the cosine button on your calculator, it spits out some number. Whatever that number is, you take that and square it. So this is a shorthand for calculating cosine of an angle times same thing. Same with respect to any function. Putting that number 2 on top of the name of a function simply means figure out what the function value is going to be and square it or multiply it by itself. So that's what this means. So remember, you have this pictorial aid to quickly tell you what the identity is going to be. Of course, it depends on your comfort in geometry to see this thing quickly. If you do see that quickly, this identity is going to be accessible to you. Alternate, well, you have to just memorize it. There is still another way of looking at it, and you see that in the text. Let me quickly mention it, and then we move on. Remember, here we had this identity, cosine square of theta plus sine square of theta equal to 1. Now, trigonometry is plagued with manipulating equations over and over again to get different looks out of them. Here's one way of one of the early versions of doing this. I can go ahead, take this equation, multiply both sides by some number or divide both sides by some number and get another one. Here, to get tangent, see, I got a sine. If I got a cosine in the denominator of this, I'm going to have a tangent available to me. So what I do is that I take this equation and I divide both sides of it by cosine square of theta. So it is mostly legitimate to take an equation and divide both sides of it by some number. Well, how does that progress? Remember, if you have something from basic arithmetic or basic algebra, if you have two numbers divided by a third number, you can split it into two pieces. That's just opposite of taking common denominator. If you have a fraction a over c plus b over c, say denominators are the same, I can add the numerator. So you see algebra practices like this plenty. Occasionally, splitting fractions become helpful, useful, and that's what we are doing. So I take this, say I split it into two pieces. First over denominator and plus second over denominator. Right hand side, I just leave it as it is right now. Now I pause and look at this thing for a moment. What is this term? Just 1. What is this term? Well, let's write it. Sine of theta over cosine of theta. We had this thing at the beginning of a semester. What was sine over cosine? If you remember that, you recognize this thing as the tangent. And right hand side is 1 over cosine and then squared. Now if you remember from beginning of semester, sine over cosine was tangent. So I have tangent squared. 1 over cosine, these are reciprocal identities. What is 1 over cosine? Secant. Now customarily, to make this thing more abbreviated, we put a 2 on top of the name of the function. This is the better notation, but it's kind of lengthy. In math, we keep making things more and more compressed. So put a 2 on top of the name of the function, but really what we mean by it is what is written here. Secant squared is the name of another function that does this. So we recovered the same information, but our approach was to start from something we knew, manipulate it, use some other facts we knew, until we arrive at the form that we want. This is kind of an approach that we are going to take in the more complicated problems. Starting problems, this geometry brings you the answer quickly. More advanced problems, you have to kind of play chess or play any of these board games. You have to kind of set the system rolling so that a few moves down the road, you harvest what you want. Okay? It's kind of actually introduction to proofs in mathematics. Okay, so far let's write down what we have next to each other. We had this one, we had this one. Item 3. For item 3, let me see if you can quickly help me to get the to the bottom of that. So again, I draw a right triangle. My angles is theta. First, we took this to be 1. Hypotenuse was 1. Next, we took the adjacent to be 1. What do you think is the turn right now? Opposite. We take opposite to be 1. Now we go through the same process. If this is 1, this is theta, what's the name of the adjacent? So here, let me write something. X. What trig function connects these three guys? Keep the x in the numerator of it. Yeah. Cotangent of theta is a ratio of adjacent to the opposite. We took the opposite to be 1, so this becomes very easy for us. So this became cotangent. Next, what trig identity connects? Let's call this thing L. What trig identity connects these three? Hypotenuse, the angle, and the opposite. Keep the L in the numerator. Very good. Cosecant of theta is a ratio of the hypotenuse to the opposite, which is just the hypotenuse. Okay, so instead of L, I can write cosecant of theta. So, now go ahead, write the trig Pythagorean identity between these three. Let me erase the irrelevant things. So, I got a Pythagorean triangle to be, excuse me, a Pythagorean identity to be applied to this triangle. You help me to write it. What should I write? So, cotangent square of theta, this leg plus that leg. Of course, 1 squared is just 1. So if you square it or don't square it, doesn't make any difference. That is equal to cosecant square of theta. So that is the third identity. And again, keep in mind, any of these things can be kicked around quite a bit. Meaning, like this one, if I want to isolate the 1 on one side, what's going to show up on the other side? Yeah, secant square of theta minus tan square of theta. If I, well, we talked about this thing plenty. This one also has an alternate form. I can say 1 is equal to cosecant square of theta minus cotangent square of theta. On the first side, this becomes overwhelming that, you know, there's so many statements being made, all of them sounding more or less same. But if you go back to unit circle and practice the Pythagorean, you get all of these things quickly. So this is item number 3. Let's these 3 are called the Pythagorean identities. Now, the other pile of identities we have seen already, but let's just formalize it and reintroduce them. That was reciprocal identities. And then we are going to take a break. Reciprocal identities. who is it that is reciprocal of sine? Cosecant. Again, notice that this can be written in plenty of ways. Like sine of theta is reciprocal of who? Cosecant of theta. Or 1 is equal to what? 1 is going to be product of these two. Is that right? Sine of theta plus cosecant of theta. So if you see this, perhaps you want to convert it to 1. Sometimes more tricky. If you see 1, it might be helpful if you write that instead of it. So reciprocal identity simply comes from the original definitions we had. Who was the reciprocal of a cosine? It could be written that cosine is a reciprocal of secant. In all of these identities, we have to take a division by 0 with a grain of salt, approach it carefully, or put it aside and say, in that case, the identity is not meaningful. Like when angle is 0 or pi or 2 pi, you'll be dividing by 0 here. That's exactly where cosecant is undefined or has its asymptotes. So when we are writing these identities, we are staying away from those trouble spots or have some fine print next to it to say, well, what's going on in that kind of a location. For other points, it's just regular mathematics. So again, here we have 1 is equal to cosine of theta times secant of theta. What do you think is going to be my number 3? So 1 over tangent. From our very starting definition, it was obvious that 1 over tangent was cotangent, or if you want to rearrange it, tangent is 1 over cotangent, which is also captured here, that 1 can be written as product of tangent times cotangent, again with a disclaimer when angle is the problematic value, like pi over 2, 3 pi over 2, and so on. So these are reciprocal identities. Now let's take a 2-minute break, and we come back and talk about negative angle identities, and perhaps go back and practice at least 1 or 2 problems on graphing of trig functions.